So as I said in the last part, once you have this partition of this transition matrix, this part P2, which is the restriction of the original transition matrix to the recurrent states, will have no role to play in the computation of this UIKs. The reason is you're going from a transient state to a recurrent state, but the first time you're hitting the recurrent state is at K. Okay, first time you're getting a recurrent state is at K, whereas P2 is about transition from a recurrent state to other recurrent state. So, but in this probability, all the transitions are from a transient state. So therefore, this P2 will have no role to play. Intuitively, this is obvious in this computation. However, the exact what is the exact form of this so-called absorption probabilities? So for that, we'll essentially just have the same partition as we have mentioned before. Let U be the matrix of absorption probabilities. Here, the UIK is essentially you're starting from I, you're getting absorbed first time in a recurrent state K, is UIK. So this, I'll write it as a matrix. And then the theorem would say that in this notation, U satisfies this equation. U is equal to QU plus R. And therefore, if I minus Q, identity matrix minus Q, is invertible, is non-singular, then U would be given by I minus Q inverse times R. So as you see, this U has nothing to do with this part P2, as we had mentioned in the previous slide heuristically, and it's also confirmed in this theorem. And in the form, whenever this has an inverse, this form also has no P2 in it. This explicit form is exactly given by this. Whether this matrix I minus Q inverse has a name in the Markov chain theory, this inverse is called a fundamental matrix. So this matrix actually plays a very important role in the theory of Markov chains. In particular, it helps us to compute the absorption probabilities. So it's important to know what is the fundamental matrix if it exists. At least important to have a good sufficient condition under which this fundamental matrix actually exists. And for that, we'll need an observation which will make it as a claim. This basically says that if you have two transient states I and j, then for every non-negative integer n, the Pijn, the n-step transition probability from I to j is same as Qn, if you take the matrix Q to the power n, ijth element of that. And this also heuristically should be obvious. This basically means, what is Q power n ij? So Q power n is just multiplication among all the transitions between the transient states, right? So therefore, Q power n ij is essentially the n-step transition probability, but the entire transition is happening through transient states. On the other hand, Pijn is that unrestricted transitions from I to j. However, since that's the important point is that I and j are both transient states, more importantly, j is a transient state. So therefore, if you have to go from a transient state to another transient state, you can never go through a recurrent state. Because once you're in a recurrent state, you will remain at recurrent states. You can never go back to the transient states. Remember, the recurrent states is a closed set. The set of all recurrent states is a closed set. You can never escape that set. So therefore, if you reach from a transient state, to a transient state, the only way to reach it is through the transient states. And therefore, these two quantities are actually equal. Okay, we'll just formalize this thing to give a proof. But this is the idea why this should hold. So, of course, for n equal to 0 or n equal to 1, there is nothing to prove. Because n equal to 0 is just, this is the p power 0 is identity matrix, q power 0 is by definition identity matrix. So I'm just saying two identity matrices are equal. So there's nothing to prove. N equal to 1 also, there's nothing to prove because q was just the p restricted to the transient state. So therefore, qij should be pij, wherever I and j are both in t. That's fine. There's nothing to prove there. So real proof is when n is bigger than or equal to 2. Now for n is bigger than or equal to 2, q and ij, as I said, is essentially transition from I to j in n steps, where all the intermediate steps are transient states. Oh, there's a mistake here. This should have been t. Okay, I'll correct this typo. Okay, all of this should be t. Okay, so all the transitions are happening through transient states. This should be all t. Okay. Now, this means you are transiting from I to j in n steps, making sure that the first heating time of a recurrent state for a first exit time of t essentially is strictly bigger than n. So this will ensure, if you keep this will ensure that all the intermediate steps are through t. So all of this should be t, okay? The typo. Okay. Now, so this probability is equal to this probability, where these are all t, by the way. Now this would be same as xn equal to j. This is because since j is a transient state, xn equal to j would mean already that the exit time of t, which is tau, is strictly bigger than n. Why? Because if xn is equal to j and tau is less than or equal to n, this cannot happen together. Because if xn is j, which is a transient state, if you have hit, so tau cannot be n, of course, because if tau is n, then xn cannot be a transient state. Obviously, tau has to be then strictly less than n, but tau cannot also be strictly less than n, because if tau is strictly less than n, that means you have already exited t, so you have already reached a recurrent state. And once you have reached a recurrent state, you cannot come back to a transient state. But here j is t. So therefore, if xn is j, the first hitting time of any recurrent state, okay, or first exit time of t has to be strictly bigger than n. Okay, so therefore, this intersection is just this set here, and therefore this is just pij. This is just a formal proof, but the idea is if you have to go from I to j, where I and j are both transient states, the entire transition has to happen. The entire path should have only transient states in it. There cannot be any recurrent state at all. Because from a recurrent state, you can never go back to a transient state. Okay, so this is what we are formalizing here by writing that if j is a transient state, then xn equal to j is contained in tau is bigger than n. Okay, so therefore, one consequence of this would be immediately, since qn of ij is p and ij n, therefore, for all transient states I and j, this is summable. Q and ij is summable. Because p and ij is summable. J is recurrent would imply that p and ij is summable, and therefore an I is recurrent along with it will imply that this is equal to this, and therefore this is summable. So only thing is I have to correct this typo. I'll correct it. All of these should be t. The entire transition should happen through transient states. Okay, so now I give you an exercise. It says that if t is finite, then the fundamental matrix exists, and it can be represented by, this means that I minus q is invertible, and the inverse can be written as sum over all the qn's. Now this sum, remember if T is finite, Q is then just a finite dimensional matrix. And then it's a matrix of order T, order of size T by T, okay? It's a square matrix of that size. And the sum is taken entry-wise. So it's just a matrix whose sum here is taken entry-wise. Now, because of the observation here that this is finite for all ij and t, this for each I and j, this is finite. So therefore, each term, each sum here is actually finite. Is entry-wise, each entry here is actually well-defined and finite. Okay. So this means that whenever T is finite, the matrix of absorption probabilities can be computed as I minus Q inverse times R. Because this I minus Q in that case is indeed invertible and it's given by this guy. In particular, you don't, even if, if the state space S is finite, then T has to be finite, right? And therefore, in that case also, it's a special case, but in that case also this form is true. And what it says is that you don't need the entire S to be finite. As long as the number of transient states is finite, you have this equation because this inverse exists. So in particular, in the Gambler's ruin case problem, therefore, the above formula, this formula can be used because in this case, in the Gambler's ruin case, the state space itself is finite. We'll do that in the next class. We'll compute this in the absorption probabilities in the Gambler's ruin problem. And then we'll give the proof of this fact. We'll give the proof of the theorem that we have seen. And by the way, in order to solve this exercise, the entry-wise sum is finite is already done. The only thing you have to show is that whatever is in the right-hand side, if you multiply that with I minus Q, that should give you identity matrix. Okay? But this is written as a sum, so you have to use a limiting argument. So basically what you do is you, instead of multiplying with this itself, you look at the nth part, you look at the partial sum of this, multiply that with I minus Q, and show that whatever you get converges entry-wise to the identity matrix. And that will complete the proof. Okay, since everything is finite and the matrix multiplication is continuous and so on, entry-wise, everything will go through. Okay, so therefore, I leave it to you. So this is a little bit of analysis is needed here, but not much. I leave you to solve this exercise. So this is where I stop. Next time, as I said, we'll first discuss the Gambler's ruin problem. We'll actually solve the Gambler's ruin problem in the sense that we'll compute the absorption probabilities in that case. And we'll give the proof of the theorem.